Well, thank you to Dinkman Jing. I'd now like to welcome Bridget, Makary, Mark, and Jordan from Nipmuc Regional High School.
Good morning, everyone. We're students from Nipmuc Regional High School. We are located out in Massachusetts, and we'd like to thank you for joining us as we present our process and exciting discoveries from the 2024 NASA High Altitude Balloon launch with MaxIQ. My name is Makary, but I also go by Meko, and I was in charge and worked with the programming, CAD design, and the 3D printing.
Hi, my name is Jorvan. I did documentation, photography, and circuitry.
My name is Bridget, and I am the coding and data analysis expert.
And my name is Mark, and I did the scientific analysis, and conclusions, and I was the chief researcher. So MaxIQ is a company that works with students across the globe, really, to help them break into the aerospace industry. And we've had the opportunity to work with them for a couple years now at this point. And one of the things that we got to do with them was actually this high-altitude balloon launch. We got to assemble our board and attach it to their payload. And we even got the chance to go down to Fort Sumner, New Mexico in August of 2024 to attach the payload. And we didn't get to watch it go up because of technical issues, but still, it was very fun. So we had a variety of science and engineering goals going into this project. Our first goal was to attach the SparkFun chip, which is a chip that is not made with MaxIQ's chip layout, so we had to figure out how to attach it using one of MaxIQ's prototype chips. Our second goal was atmospheric monitoring. We wanted to collect a lot of data on the atmosphere and compare it to what we've already seen and ask, is this expected, is it not, why or why not? Our third goal here was resiliency in our data recording. We've had issues in the past with corruption due to starts and stops, so we wanted to make sure that that would not happen while the chip is several 100,000 feet in the air. And modeling climate change. We wanted to see, how does this data compare to climate models? Was it expected? And can we use this data to predict the climate in the future?
So here we have our payload design and the components we've selected for it. And given the limited space we had available, we had to be intentional about the types of data we wanted to collect. So ultimately, we decided to collect and monitor CO2, hydrogen, ethanol, and the volatile organic compounds using an air quality sensor. We also included a light sensor to measure ambient and UV light, a temperature sensor for temperature and humidity data, and a BME 688 chip, which was not developed by MaxIQ, but by SparkFun instead. And this was used to detect gases, the gas resistance in the atmosphere. To power and operate all of these components, we used an extended core, and this was connected to a CPU, or this acted as a CPU and was connected to a USB chip to enable power and programming capabilities. However, during the assembly process, we ran into a challenge with specifically the BME 688 sensor, which wasn't directly compatible with the rest of the components. So to overcome this, one of our group members, Bridget, learned how to solder and connect the BME 688 sensor to a MaxIQ prototyping chip. This allowed the whole chip to be compatible with the system. And with everything connected and functional, the payload was ready to launch into the atmosphere. We had two 3D printing components as well. The first was the payload housing in general, which had three separate levels. The first level contained our chips and other chips from other schools that worked with the MaxIQ payload. The second one contained hand warmers to make sure that every component works and stayed warm in the atmosphere. And the third was a battery pack to make sure they were all powered. We had a cover on top of all of this to make sure no debris and other things got into the payload, and three openings to allow gases and light to enter into the payload itself and data to be collected from the sensors. The second component, which we did not use unfortunately, was a cover for the light sensor to allow light to funnel in and get a more accurate reading from the light sensor. This was not used since we had a problem with the 3D printing process, and the filament was much too thin to stay onto the sensor. So every time we attached it, it would just snap.
One of the most important and impactful aspects of a project is being able to see it through its data analysis, which ended up being one of the most interesting parts of our project. I analyzed the data with Python to create graphs which visualize the atmospheric conditions of the balloon. Our pressure and altitude versus time graphs almost perfectly aligned with our expected results, and this gave us a point of reference for the rest of our data. I applied a colorful cluster analysis, cleanly demonstrating the transitions between atmospheric layers. And it was also interesting to see the increased scattering of points over time on the altitude versus time graph, indicating the high speeds at which the balloon fell after it popped. As the balloon increases in altitude, the temperature is expected to decrease through the troposphere, remain constant in the lower stratosphere, and then increase through the upper stratosphere. For the most part, our temperature data does align with these expectations, but our more in-depth analysis and the graph on the left with the section in blue reveals high temperature variations during the balloon's float time. This was our first indication of an anomaly and will be further explained later on. The average hydrogen and ethanol recordings in our data are relatively what we expected, and they line up with the average increases over the past 20 years. However, we do see one specific anomaly where both hydrogen and ethanol sharply decrease towards the end of the balloon's float time.
So interestingly to note about ethanol that I thought was very interesting is that the amount of ethanol in the atmosphere has increased a lot over the last about 40 years at this point. And that's due to a lot of different legislation. I put up there the Clean Air Act amendments of 1990. There's a bunch of other ones too. The increase in ethanol in the atmosphere can have some effects. Ethanol creates more products when it is used than gasoline does, which thickens the atmosphere in some places. And it also can react with light from the sun and deplete the ozone, but this is not a common thing to happen. But interesting to note that as we use resources on the ground, we affect the chemistry in the air and in our atmosphere, which can change the equation for things like rocket fuel, how it interacts with our atmosphere, or other sort of combustion reactions.
The carbon dioxide recordings were the first measurements that did not remotely line with our expectations. In the stratosphere, carbon dioxide is expected to remain low and relatively constant. However, our sensor recorded a large spike in carbon dioxide in the upper stratosphere, and it actually hit our sensor's maximum measurement ceiling. With the Google Maps 3D model of our carbon dioxide data at the bottom, we can see the high levels indicated in red occurred over a distance of 26.58 miles between two mountain ranges just south of Albuquerque. At this point, we definitely started to realize the balloon encountered some kind of stratospheric intrusion. Our UV index data was another major indication of a stratospheric intrusion. As the payload gets closer to the sun, it was expected that the UV index would increase along with the balloon's altitude. Instead, we see the UV index decrease and remain right around 0, and this negative spike perfectly aligns with the carbon dioxide's positive spike. Our gas resistance and volatile compounds data were our most anticipated results because we did not have as much previous data to compare it with. The volatile compounds visuals on the left indicate high levels throughout the entire upper stratosphere. However, we predicted would spike even higher at the same points as carbon dioxide if the volatile compounds had not hit the sensor's measurement ceiling. Low gas resistance indicates low air quality. So looking at our gas resistance graph on the right, we can see our sensor picked up very poor air quality readings, once again, exactly when that carbon dioxide spikes. So we came to the conclusion that the balloon definitely interacted with some kind of stratospheric intrusion because the anomalies we saw were recorded by multiple sensors across multiple teams, and they all line up perfectly with each other. We researched exactly what this intrusion could be and discovered that volcanic emissions are actually the most plausible explanation. The composition of volcanic emissions would explain the spike in CO2, the low UV index, the high levels of volatile compounds, and the poor air quality, all visualized in our data. Additionally, the high levels of sulfur dioxide in volcanic emissions would interact with hydrogen and ethanol in the atmosphere and would result in the negative spikes in our data. Although there are no active volcanoes in New Mexico, the most recent and closest volcanic activity to our balloon came from the Great Sitkin volcano in Alaska.
So, after discovering the volcanic activity from the Great Sitkin volcano, we started to look at jet stream data and volcanic emissions models to determine if the volcanic emissions could be the stratospheric intrusion that our data picked up. The trajectories of the volcanic emissions line up with the jet streams. Both of them show them heading towards the southwestern United States. We could not find volcanic emissions models for the time of our launch. However, since the current emissions models follow the current jet stream models, we can reasonably conclude that the volcanic emissions follow the jet stream before the launch into the southwest United States. Okay. All right. Further research led us to density maps of sulfur dioxide and sulfate from NASA's Global Modeling and Simulation Office.
So in the atmosphere, the oxidation of SO2 creates sulfite and sulfate, which is a reaction that also occurs at higher temperature and humidity levels. But specifically here, the SO2 emissions could cause cooling in this area as the SO2 is better at, and the sulfate is better at absorbing the solar radiation and also scattering it, which would also cause a decrease in our UV index, which does line up with the data we collected.
So the density maps found online demonstrate high levels of SO2 and sulfate that emerge directly from the Great Sitkin volcano and then travel to the southwest United States. These readings occurred a week before our launch and could explain the negative spikes in hydrogen, ethanol, and the UV index, which occurred in our data. High levels of SO2 and sulfate also traveled over from East Asia and could have contributed to the data readings. However, the appearance of these compounds over the Great Sitkin volcano still supports our original hypothesis.
So being part of this project and the NASA HAB launch, I think we can all agree was an amazing experience. We were able to learn so much, grow as a team, and had the chance to work on an amazing project that was really unique to us. We were truly grateful for the opportunity to be here and to take part in a project like this. We'd like to give a big thank you to MaxIQ and the National Defense Industrial Association for sponsoring and supporting us throughout the journey we went through. Their help made all of this possible and is why we're here. And of course, I'd like to give a huge thanks to Mr. Gorman. His guidance, support, and most importantly, his patience meant a lot, and we couldn't have done it without him. This experience is something we'll carry with us for a long time and definitely use within our future career paths, no matter what we choose to pursue. Again, thank you all for listening.
And we would love to answer any questions. Yeah, we looked into multiple possibilities, like military testing as well. The region specifically, like the high altitude balloon crossed entirely over a desert where no one really was. So we definitely looked into multiple possibilities, and we're wondering if it just hit a patch of CO2. But combining it with the rest of the data and the same spikes, we found that volcanic emissions were highly likely.
And it is important to note, though, that one of the things we did also look into is that there was military testing in White Sands, which was rather close, about early August, which the balloon took place mid-August. So it is definitely a possibility because we did look into what jet fuel contains, and it's pretty similar. We decided that volcanoes seemed more likely just because of the UV index decreasing and the high concentrations of SO2, but there is definitely alternative solutions to this problem. It's the only thing we know for certain is that there was something in the atmosphere at that time that blocked our data.
We've also talked to multiple professionals, and like it could be a combination of things, but yeah. Any other questions? No. Thank you so much.
Thank you. If you have any more questions, we'll be out in the lobby, and we'll be available throughout lunch as well. Thank you, guys.
Thank you.